This is a view of the Earth. It's really a composite picture put together from satellite images. And what it shows is the light from the urban centers in the various countries of the world. You may notice that in Central Africa there's virtually no light pollution, as well as in Central South America, and in large parts of China and some parts of the former Soviet Union, as well as, interestingly enough, the middle of Australia. But notice the populated coast of Australia and almost all of India, the Japanese and Korean area, all of Europe, Western Europe worse than Eastern Europe, and down into the Middle East, and then the coasts of South America, and basically the whole eastern half of the United States, as well as the state of California, and to some extent down in Mexico. Heavy light pollution. So one of the things that motivated the development of filters for telescopes was an attempt to try to reduce the effect of light pollution. And if you've ever looked up in the night sky in an urban area, you know that there is a reflection off of the moisture in the atmosphere. No matter how dry it is, if there is any amount of moisture in the atmosphere, in other words, if the relative humidity is anywhere above 15%, the light from the ground reflects off the atmosphere. So even if you're looking straight up, you're actually seeing some of the light from the cities. Now, as you get out into very dark areas, I have been out in the area of Fort Davis, where the McDonald Observatory is located, and out there, they have very, very dark skies. So, one of the purposes of filters is to reduce light pollution. Another purpose is to enhance contrast. So to understand both of those, the first thing we have to do is take a look at the visible spectrum. This is a composite view of the visible spectrum. That is, the spectrum that our lights or our eyes are most sensitive to. And our eye is not equally sensitive to all of this. Actually, most of the sensitivity of our eye peaks in the yellow and green region, and that's because that's where sunlight is mostly. Yellow, of course, sunlight. Green occurs a lot in plants because of photosynthesis. So if you want to survive in the jungle, this is where you want to be able to see the best, and that's why our eyes are so good at that area. On the far right is red and eventually infrared, in other words, past red, and that is a wavelength of about 780 nanometers, or a frequency in terahertz of about 380 terahertz. On the left is violet, which is around 400 nanometers, or a frequency of 750 terahertz. This graph is the photon energy. In other words, a photon with a level with 2.1 electron volts of energy is emitting light in this area between yellow and orange. Similarly, the highest energy photons are in the violet region, and of course the ultraviolet are even higher energy than that. So why do we care about this spectrum, other than the fact that this is what our eye... This is the spectrum of a high pressure sodium lamp. Once again, red on the right, violet on the left, and you notice that there are some peaks. This is the spectrum, and by the way, these lines just show a particular wavelength, but this is the spectrum. Notice that there are large parts of the spectrum here where there is little, if any, output from a high-pressure sodium lamp. So if you have high-pressure sodium streetlights, for example, and many of them are, in parking lots and along streets and highways. It suggests that maybe if we could filter out some of this part of the spectrum, we can reduce the pollution in our telescopes due to high pressure sodium. And this has led to the development of filters. And generally, the filters that are intended to reduce light pollution fall into three categories. The first is the so-called LPR filters, or light pollution reduction filters. And you notice that what they do is they notch out the area where the sodium and some other light sources tend to work. So-called narrowband nebula filters, and we'll talk more about those, why that you can get away with this kind of filter. And then finally, what are called line nebula filters, and normally these are referred to as oxygen filters or O3 filters. We'll talk about where that terminology comes from. But the type of filter and whether it will work in your particular situation depend on a number of factors. This is the same graph we saw earlier, but I have now drawn in orange a set of lines that are due to oxygen 3. Once again, we'll talk about that. Hydrogen beta, this line. And then over here on the right, hydrogen alpha, this line. And to the right of that, two lines that are sulfur 2, S2. Now, where do these numbers come from? Well, if you look at the structure or at the energy levels of an atom, you'll discover that there are a number of shells. And the way that photons emit are produced by energy changes is when an electron moves from one shell to another, it either absorbs a photon of a particular energy or it emits it. And that's one reason I showed you earlier that it has to do with the energy of the photon as to what frequency. I realize this is getting kind of deep into physics, but the whole idea is that if you have an oxygen atom and there is an electron in the third shell that drops to the second shell, it will emit radiation in this area. Similarly, sulfur in its second shell, if it drops from the second shell to the first shell, it will emit in this area. Hydrogen emits different areas depending on the particular energy that the hydrogen atom is at. And all of these are lines or frequencies, colors if you will, that are emitted by stars. Now, in stars, there is an atomic process going on. Some fission, but a lot of fusion, where, for example, hydrogen is being fused into helium. In the process, a great deal of energy is produced, and so starlight tends to be where these orange lines are. Now, before we talk further about this, we do need to understand the difference between continuous spectrum, line spectrum, and absorption spectrum. Here are examples of the three types of spectra. Now, the top picture depicts what is called a continuous spectrum. Sometimes this is called black body radiation because it is simply the radiation that comes off of a hot object. And by hot, that means anything above absolute zero. It doesn't have to be hot. In other words, it can actually be cold to the touch. It still emits a spectrum. Obviously, it emits more energy the hotter it gets. But this is a continuous spectrum. Notice that each color, if you will, or each line, each frequency blends into the next. It is a continuous spectrum, and it follows what is called the black body law. We're not going to get into optical physics here, but this is just a hot object. So a piece of iron, for example, in a fire, will start out, initially you'll see red. Now, of course, it's actually emitting below that when it's, even when it's cold. There are frequencies that are being emitted. But it turns first red, then yellow, and normally you don't see the green, but if you heat iron up hot enough, it will actually look blue. And if you've ever looked at the flame, you notice that the cooler flames look yellow, the hotter flames actually look blue. Those are black bodies. The second kind of radiation is the emission spectrum, and at the bottom is an emission spectrum. Notice that on the right I have the hydrogen alpha lines. That is around 656 nanometers. And on the left are the hydrogen beta. These are the primary emission from stars. Now there also is a hydrogen gamma and a hydrogen delta. These have to do with nuclear processes. In the middle is what happens when you shine an emission spectrum through, or a continuous spectrum through, a gas. A cool gas that is sitting between you and the stars will absorb frequency. So just as the star emits hydrogen alpha, the cool gas, if it gets in the way, will absorb it. And astronomers use these various properties to determine what the elements are in a star or in the gas around in front of a star or a nebula or whatever they're looking at. One of the filters that we'll look at a little later, an 1.25 inch filter, is an O3 or oxygen 3 filter. The many nebula emit oxygen 3 lines. And so what this particular filter, this actually is one by Astromania, it's called their O3 filter. And the blue curve shows the pass band. In other words, this 100% would be at the top, all the light coming through. Completely dark would be at the bottom, no light getting through. Notice that it only passes this very narrow band of frequencies. Those happen to be the frequencies around 500 nanometers, which is where O3 is. When we get to the practical part, we'll explain why you might want an O3 filter. Another filter that we're going to look at is called a moon and sky glow filter. And this filter, notice it passes a lot of the light down in the green, from the lower part of blue through the green, but then there is an area where very little light is passed through, and then another rise. Now, the scale here is a little different. On the left is 300 nanometers. Visible light, that is what you can see, starts at around 400 nanometers, and normally goes up to a little above 700. So your visible, what your eye can see in bright sunlight color, is from about the left to the right of this filter. But notice that there is an area that takes out, and this particular area is the area that the high pressure sodium and some other lights emit the most of their energy. So the reason that it's called a sky glow filter is it's intended to remove the effects of certain kinds of street lights while not affecting the rest of the image very much. Another essentially sky glow filter is made by SV Boni, a company I mentioned a couple of times in the eyepieces category. They also make a filter they call a moon filter. In a minute, I'm going to distinguish another kind of moon filter. But basically, it is very much like the one you just saw. Notice in this case, they start at 300 nanometers. The visible light, most people's vision starts closer to 400 nanometers, and normally goes up to about 800 or a little higher nanometers in the infrared. Notice that it has the same very low transmission in the area of the high pressure sodium, but it tends to produce a bit more here, then it takes another dip and a third dip, and then goes out into the, actually most people can't see anything out in this region, but photographic film or charge coupled devices, CCD cameras, can see things out here. So this is roughly the spectrum of, or the absorption characteristics of the SV Boni filter, which we will look at in the practical part. Finally, I would like to talk about another kind of filter that is called a moon filter, but it is not intended to filter out moon glow. It is intended to reduce the intensity of the moon. And there is, some people get confused, particularly when they look online and they see something labeled a moon filter. That can mean two entirely different things. It can mean that it is intended to at least partly reduce the effect of moon glow when you are looking at something else. So suppose you're looking at the Orion Nebula and the moon is out. Well, some filters try to reduce the effect of that moon glow on your image of the Orion Nebula, for example, whether it's visual or photographic. They work to some extent. But there's an entirely different kind of filter called a moon filter, which is actually a neutral density filter. And all it does is darkens the amount of light coming through the lens. The one that we're going to look at later, I think, has a 13% transmission. Now understand, it doesn't filter out any particular frequencies. In fact, it tries to pass all light equally. It just reduces its intensity across the spectrum by, in the case of a 13% filter, 87%. So in other words, only 13% of the moon's light comes through. Why would you want that? Well, if you look at the moon directly in a modern large aperture telescope, like the Meade LX10 or the Celestron 8SE, the image will dazzle you. It will, it will literally cause your eye to react. And when you see someone that has been looking at a full moon in an eyepiece, and they step away from the eyepiece, one eye is a very, very tiny dot. It looks like they're on opium. And the other eye is completely dark adapted and wide open. And the purpose of a neutral density filter, which we will look at, is to reduce that effect. So it doesn't impact your eye quite as much, and you can actually see a little more detail on the surface of the moon, particularly as the moon gets more full. So that is the bulk of what we're going to look at. We'll also look at some color filters that are intended to enhance the detail on certain planets, like the belts on Jupiter, the Great Red Spot, in the case of Mars, the features on the surface, the red features, and so on. But once again, we'll look at that when we get to the practical phase. So, for this sermon or this lesson for the day, how do they say it? Here endeth the lesson for the day. This is the theory that I'm going to present. In the next part, we will talk about the actual filters, and we will look at them and how they attach to the telescope. And primarily, we will be looking at them from the standpoint of a visual astronomer not astrophotography. So I hope you'll look forward to that one, if you haven't already skipped this one and jump forward to that one. And we will see you there. And in the meantime, have a nice day.